pavement performance, roadbed soil, slab characteristics, liability, standard deviation, traffic, load transfer, strength measure, and thickness instead of structural number. So this the concept of serviceability index is same, except for flexible pavement we use 4.2, but for rigid pavement we use 4.5. The terminal serviceability is 2.5 or 3. So delta PSI will be now 2.0 or 1.5. Usually, we don't recommend rigid pavement for the local road. That's why we are using either 2.5 or 3, meaning at least arterial we are designing as a rigid pavement. So this is a typical PSI curve where P0 here is 4.5, PT is either 2.5 or 3, and delta PSI, as you know, change in serviceability index. Now, unlike Aashto flexible pavement design, the subplate strength is evaluated by means of plate load test, in which there is a plate. The plate can be either of the 12-inch dia, 18-inch dia, 24-inch dia, 30-inch dia. It is being loaded. You can see it is just like you see if you are changing your tire, you can use this jackhammer. This jack, there's a plate, and from this jack, and this is a loadometer, and deflection there is somewhere else on the plate. Once you load this thing from here, you have this flow meter over here where you estimate the deformation. At 3 dials are there. So this is the head, there is a roll direction, and this is the pressure gauge. So this now once you load this thing, you can calculate the K value. There is a relation. This is not shown here, but I will tell you this relation is K is equal to 1500 CBR over 26 power 0.77, I guess. So this, if you don't know K value, you can always estimate from CBR. Now, once you know this K value, then the slab value, the value of PCC slab, that will be resting on your subbase, and the subbase will be resting on the subplate, as you know, the pavement section. So you estimate the flexural strength of the, you assume that flexural strength, and the flexural strength of the slab is dependent on elasticity modulus. The flexural strength of the slab is estimated by 7.5 square root FC dash, and it is usually between 500 to 750 psi. There comes the elasticity modulus, EC. EC is 57,000 square root of FC dash, and it is between 3 million to 4 million usually. The next step pardon me. Once you know, then you have to estimate, if you have a K value 50 PCI as measured from that test, and if you have 4-inch subbase, then your value will be, for the value you will use in your design will be 65. This is for untreated subbase. And for instance, if your value is 100 and you have assuming the 9-inch subbase, then your K value will be 160. Actually, in a rigid pavement design, we assume the thickness of subbase. We don't calculate subbase thickness. We assume it ourselves. Normally, a 6-inch subbase is provided for a rigid pavement. So once you provide a subbase, already the provision of subbase will improve its bearing capacity of the subgrade soil. So if the subgrade soil has a modulus reaction of K, say 100, and if you're providing 6-inch subbase, then it will be actually the design value you will take in the equation will be 140. If you have estimated 50, then it's 75. And if we have a K value of say 75, then obviously you will take the average between 75 and 140, and what is that value? Whatever is the value is your design value for the rigid pavement. Now, if we have a cement-treated subbase, you know that's what is the difference between cement-treated subbase and treated base, untreated. So if you are using a 6-inch treated base, your value will be 50, and you will have 230. You will use 230 if your K value, and if your K value is 100, you can use 400. So this is how you take the subgrade value. Unlike a flexible pavement, you will just estimate and you will use it in the design. Here, we actually don't take the K value directly, and we modify it because of the process of the subbase. Now, next thing is the reliability. Again, the reliability level is taken as 95% for urban roads. We are allowed 80 to 99.9, but we take around 95% reliability. And principal arterial collected, though we have a value for local, but since I have suggested that you don't prefer a rigid pavement or a local road. Standard deviation. Standard deviation is accounted for poor traffic condition, material variability. This we already had discussed in flexible pavement. Construction variability, supervision, and this should be selected. So for rigid pavement, it is between 0.25 and 0.35. Usually, we take 0.35 as our value, right? 0.35 for a rigid pavement. No, so the traffic characterization, it is the loads are estimated the similar manner that we have done in the flexible pavement, and that's why we are not explaining you the new calculation is the same. Then the drainage coefficients. The drainage coefficient is the same as for flexible pavement. And usually for Pakistan, I said that 0.8 to 1.0 is used. 0.8 when you have a very wet condition, or you are designing a road along the seashore, or in an area where there is more humidity, more moisture, and 1.00 if you are designing in a desert or the area where we have a less rainfall. Then, in my explanation of this subject, I have told you there are different types of slabs, and these slabs are connected with the dowels, and that value of dowel is also taken into consideration while designing a rigid pavement. Usually, a value of 3.2 is taken as a standard, and if you can have this thing, but for the sake of this class, and actually for the sake of the practice, 3.2 is good enough value to be taken. Now, Once you know this thing, here we will use again the same equation, the same thing. It's a trial and error, where left side, you will take the value of left side, W18 is the traffic results, and on the right side, you will take these values. Now, ZR will be dependent on reliability, standard deviation 0.35, T is not known to us, delta PSI 4.5 minus 2.5 or 4.5 minus 1.5, and then again T is not known to us. Then we have PT is 2.5 here or 3.0, T is again not known to us. SC is the modulus of rupture that was between 500 to 750 psi. CD is a drainage coefficient, and this is taken as 1. TC is elasticity of concrete between 3 million to 4 million, and K is what you have calculated and modified for your base. I have explained you that if you have whether you are using 6-inch base, you are using 4-inch base, with a particular K value you have calculated or estimated from the formula, you get modified, and you put this thing to make trial and error so that the left hand side equal to right hand side. This is how you use the equation. All I think is explained to you now. Now let's take an example. The example is, for instance, we have a K value. Now I'm taking this modified K value of 260 psi, PCI. Elasticity moderate is 5 million. This data is given to you. Modulus of rupture 650 psi. Darwin coefficient 3.2. Standard deviation 0.35. Reliability 95%. Delta PSI is 1.7, 4.21. And if I assume the traffic is 26 million, you have to use the nomograph to calculate the thickness. Here, in this rigid pavement, you have two graphs, right? First, you will know the effective volume of modulus of subtraction. That is 260. How 260 you will estimate here? You see this thing. One larger bar is 100, and this becomes 200. This becomes 300, 400. Actually, this is 500, right? Then 600. 600, 700, and 800. So this is 500, right? And this is 200 because this is a logarithmic scale. That's why you won't find values to be regular as a normal scale. So because it is based on the log scale, that's why you will find the distance between 100 and 200 more than distance between 300 and 400 or 400 and 500, right? Since I have a K value of 260 psi, so I estimate this 220, 240, and 260, I draw perpendicular. Now this curve is my elasticity modulus curve. So I stop at 5 because the 5 was given to me. Then I go perpendicular. I stop here. My modulus of separate reaction is 650. So I join this point with 650 extended to the transfer line. I stop here and I know my load coefficient, that is 3.2, 3 and 3.2 somewhere here. I connect this point with this point extended to the transfer line. I will stop here. Now, since I know my drainage coefficient is 1, so this is the graph for drainage coefficient. So I join this graph and I stop at this value. This is around 70. Right. This is page 1. I'll start once again. I had value of 260 PCI. This is 200. This is 300. So 260 may be between here and here. So this one, can I say this is 220, 240, and 260. From 260, I'll go perpendicular. I stop at this curve. This is elasticity modulus of concrete curve. The elasticity modulus concrete curve in this class, in this sample, is given to me as 5 million. I stop here. I will go perpendicular and stop at this point. Now, there to go ahead, I have to join this point with a modulus of rupture. That is 650. So I know this is 650. I join this point and extend it and stop at traceable line. Actually, we always join in a nomograph, we join 2 points and extend it to the third point. Project it to the third point. Now from this point, I know my load transfer coefficient. I'll connect this load transfer coefficient, this point, and extend it to transfer line once again. Once I have done this, I go further into the graph and I find 1.0 here. I connect this line with 1.0, extend it to this line. This is the mesh line that is around between 60 to 70. So it's around maybe 68 or 69, right? The nomograph does not end here. We'll start on the page 2. On page 2, we had actually 68. We stop at 68, so start with the 68 on the mesh line. And what I am going to do is to connect this point with the design serviceability delta PSI and then stop here. And then I'll draw a perpendicular right from here. Now, I cannot go further. I will now start from the bottom. Reliability to standard deviation, stop here. Standard deviation to this traffic. And I pardon, this is a problem here. I feel there is a problem with connection. So let me share with you what happened here. There's a slight mistake. Actually, what happened is, it's not like this. This point, actually, when I say I'll just keep on extending this line when I go there, right? And here I'll extend this line to this corner of the slab, right? And once I do this thing, then once I stop here, I will draw a perpendicular, and let me show you. I'll start my perpendicular and I'll stop here, so that I can see that this is my point. This is my actual thickness. So my thickness is around 12 inches. So this is my answer. Okay, so once I have done this thing, now what I'm going to do is, let's wait for the slideshow. So my thickness is 12 inches. Pardon me about this mistake. And then I can know that the value is the required slab thickness 12 inches. That's how I've calculated. I again can start. Once you stop at 68, you stop at 68. Join design serviceability delta PSI. Stop here and draw perpendicular out of this graph. Now you cannot go bottom. Actually, then you start from the bottom. Reliability to the standard deviation 0.35. You stop here. And then from transfer line two easels, extend this point here. And once you do this thing, draw perpendicular, and then you will find this line as the value of my thickness. Normally, the minimum thickness is 8 inches. So if you come out with the value of graphic has got more than 1 million, your minimum thickness is 8 inches, so we have 12 inches thickness. And if you have driveway, then it is 6 inches. This is some rules for designing your rigid pavement. So this is all about rigid pavement. In a little while, we'll start runway pavement design.